Okay, hello everyone, and welcome back to the AutoML seminar. It's my great pleasure today to introduce today's speaker, Richard. This is actually the second time we have Richard at the AutoML seminar. The first time he gave a talk on open source Visier, and if you haven't seen the talk yet, so please definitely check it out on our YouTube channel. Richard is a senior research scientist at Google DeepMind, working on a variety of topics, including AutoML, but also reinforcement learning and robotics and transformers. And today he's going to talk about his latest work, OmniPred. And yeah, with that, welcome Richard to the AutoML seminar again, and please take it from here.
Yeah, thanks for the introduction. Hi, everyone. So this OmniPred work is in joint work with Google DeepMind folks and also our student researcher Oscar, who's in the call from CMU. But this is also part of a larger effort generally to apply, LLMs to black box optimization. So with that, I want to feel free to ask any questions, interrupt me. This is trying to be informal, but so to begin with, right? Let me first talk about the current state of ML. So right, everybody knows ChatGPT and hopefully Gemini by now. The thing with these chatbots, right, is that they're all based on RL fine-tuning. And the thing that I want to point attention to is this thing called the reward model that's used heavily in RL fine-tuning. The idea there, right, is to just simply be some sort of like human imitator to rate things that human would say will like also rate, right? And so this is what's called RL from human feedback, where humans dictate subjective ratings such as creativity, personality, safety, human verifiable factuality, right? Like who's the president currently of the United States, something like that, right? And a lot of times these scores are basically either like ordinal, like it's, give me a rating between -5 and 5, or it's like a pairwise ranking, right? And this is generally speaking great for human interaction, where like the goal is trying to make your chatbot be good at writing prose, like poetries and essays, right? Make it have good conversations, and generally overall be like likable and have human values. But this is poor for things like experiment prediction, business metrics, and forecasting, right? If you ask a human, like, can you predict the outcome of the experiment? They would not know what to say, and it's pretty inaccurate, right? That's why we run the experiments ourselves. And so you can sort of see that from reward models from the AutoML lens are really just like language model regressors over black box objectives, right? The current focus is hugely on human feedback, where we, like have these like human raters, like Amazon Turks, right, rating these essays. But this could be extended to any black box function. So for example, as we're all AutoML researchers, outcomes of expensive experiments, synthetic or mathematical expressions, metrics over production systems, or environmental feedback, right? And to just hammer this down even more, there are different names for different communities, right? For the LLM lingos, it's like reward model, auto rater, whereas AutoML folks, it's called regression, performance prediction, surrogate. And so for regression with language models, the idea here, right, is that maybe it's possible to, given a prompt, it's like I'm training a resident on CVAR10 with these hyperparameters, predict the accuracy, and then the model actually predicts some sort of numerical score, right? And so regression and experimental design, right, would be like X are essentially the parameters to black box function. They'd be like floating points, categories, or integers, and a Y being a scalar metric like accuracy, right? And so the benefits of this, in at least for the LLM community, is that you now have reward models simulating systems or nature, and also the fact that matters most reward models currently in their domain are like really not numerically precise. They're all just like, give me a score of 0 to 5 or something, right? Just like Yelp, how you rate Yelp with like stars, right? That inherently has a lot of problems, right? And this might be useful for things like stock market prediction or world news prediction. But also for the AutoML community, you might be able to have like a flexible text-based regressor. This allows a lot of like multitask and meta learning, and also possibly the reward models being like surrogates of humans. You also have more realistic surrogates of like black box objectives, like AutoML objectives, right? So yeah, before I dive into details, are any questions before?
How would you define a reward model? So is it always a LLM that just does the output in regression, or is it also LLM plus something else that does the final rating?
So usually it's almost always something that like outputs a score, right? So it's like basically 0 to 5, the integer 0 to 5, or just like this essay is better than that essay. So it's some sort of pairwise ranking that you can deserialize out back into Python. There are some more reward models that like can explain the reasonings behind them, but like I might want to like let's avoid that kind of issue for now. Yeah, so they're really just regressions. Like they're exactly the same as what we've been doing in AutoML, but for like just AutoML domains. Yeah. So yeah, anything else?
Yeah, so just a clarification. So the reason that they're called reward models is that they're trying to mimic what a human would allocate as a reward to this, right? And technically, they are just regression models, but the target typically tries to mimic a human. Is that sort of a distinction that could be made, or?
Yes, because the idea in RL fine-tuning is that you want to perform a policy gradient over your pre-trained language model so it optimizes some objective, right? And technically, you could do it with any synthetic function that's fast. Well, right, you can't run an RL loop where the environment is like actual humans giving the reward. That's too slow. So they have to make a regressor that like imitates them so it's much faster. That's really the only reason they're doing all of this. Yeah, I hope that answers the question. Yeah. So I guess we can now dive in details, right? So at least for us, right, this is really just based on standard reward models in some sense, but there are some slight modifications. So the first thing, right, is that if you ever touch the language model, there are basically a prompt and a response, right, in standard prefix language models. So in our case, what's going to happen is that the prompt is going to be X and M. X is basically the function input. M is like the metadata describing the function. And then Y is the objective value, right, some numerical score. But this paradigm is very different from like what's going to happen in normal regression. So the first thing is, when you serialize X, okay, it's in natural language or JSON, right? That's the first thing. Second thing is that, right, because it's a string, it allows variable lengths and also allows basically, it doesn't matter how many parameters are in your X, right? This is important because normal regressors require X to be turned into a tensor first. That gives you a lot of problems with like fixed length and whatever, right? Last part, importantly, is that this is in raw values, right? I'm not normalizing, let's say like batch size being 128. I'm not going to normalize that number to like 0 to 1. It's in raw values, which means that it's not like it's not specific to the search space of this study, right? This is important because ideally any regressor should ignore what the boundaries of the search space really are, right? Like you specify X being like between 0 and 1, or like X between -5 to 100. It doesn't really matter in this at the end of the day. That's like a human artificial construct, right? So this avoids all of that. And for serialization on the M, right, this is just natural language. You can shove in anything. So this is intended to sort of condition the output distribution and sort of allow the language model to identify what study am I in, right? And so the M can be, for at least, contain things like username, the title, objective, things like that. Or you can even stick in like some just numeric ID if you want the language model to identify which study it's on. So lastly, the Y values, right? So this is going to be based, you could represent it using like normal human serializations, but the problem is like those are not fixed length tokens. And that causes problems during decoding. So instead, what I'm going to do is represent the number as a fixed length custom tokens, right? So basically for us, it's like the sign has a special token, mantissa, a few mantissa tokens, and an expo token. And then during inference, we're going to perform restricted decoding where like we're going to mask out the logits so that it always outputs the right tokens, right? So for example, the very first token is supposed to be a sign token plus or minus. I'm going to mask out every other logit in the vocabulary so that I can force out this plus or minus and let the model decide, right? Yeah, so always outputs correct tokens. And again, this is in raw value. There's no normalization. This is also extremely important to allow you to do multitask training so that you're not like specific to a certain study, right? And so, yeah, like I said, this is sort of like a regression paradigm change. So the first one is it allows dynamic input spaces, right? The X serialization ignores search space bounds. And whereas like every other baseline essentially requires you to normalize it into some sort of like 0-1 tensor, we don't have to, right? And multitask learning, well, just look at M, right? Right, and as I said, like there's no need for tensorization. You don't need to deal with fixed length embeddings. This causes a lot of problems with like multitask training, right? With a lot of people. And lastly, you don't need to rescale or normalize. So this avoids numerical instability issues, right? And, yeah. And so the question is, well, like, what about new studies? Right, you need to deal with that, like for regressor guided search or any other application, right? And so for this one, this is a bit controversial, but basically, here we want to absorb new data using gradient updates, not in context learning. So what we're going to do is like we're going to pre-train the model over some corpus of data, but fine-tune it over any new XY objectives, right? And you can make this even more efficient using LoRa. And here's another thing is that this is not a large language model. This is a customized language model, which is just a basic 12-layer T5X encoder decoder, only 200 million parameters. It doesn't understand English at all. It's not pre-trained on English. And this is like really cheap, actually. It's like you can train it with 8 GPUs and use 1 GPU for inference. That's really it. So that's also to emphasize, this is not a large language model. Yeah. Before I go into data, any other questions?
Yeah, so about the data you feed in there. So this is really, do you make any assumptions on how the hyperparameters should be named or so? So is learning rate always called learning rate, or do you sometimes call it, I don't know, learning rate atom or something like that? Or
right. So like the idea here is to emphasize the user should be lazy. So like literally what we did was just JSON the dictionary and never do any like processing of that. And like, right, yeah, the intention here is ideally the user should be lazy. The lazier you get, the more this becomes of use to you. You could do some pre-processing, hopefully, like maybe making sure the names are similar. But I want to emphasize, right, the philosophy, design philosophy of here is like being lazy. Yeah.
But if you're lazy, why wouldn't you want to use a large language model? Because large language models would just know directly, yeah, LR or learning rate, that's the same thing. And if you don't pre-train on that sort of information, it wouldn't know it. Also, if you pre-train on the internet, then yeah, you would just know what a CIFAR 10 ResNet should give you. So yeah.
Yeah.
Curious
So
what you say.
yeah, so this is a design choice in the first paper we had to make, which is just like to keep it really simple and like so that there are minimal requirements as much as possible. Let's just try it where like it's starting from scratch, right? Because there's going to be confounding factors on like how big is your model then, and then like what data has been trained on. Like I want to reduce the requirements first, and I think some of the results might surprise you in this scenario actually. I do think, of course, if you did have English pre-training, it might help. The caveat is actually it might. I'm not actually sure it might truly benefit you. I'll show you why in experiments. But yeah, yeah.
one more question regarding the input. So just to make sure, so you feed essentially one hyperparameter configuration at a time. So you don't feed the entire sequence of hyperparameter configurations like you did for
Correct.
outperformer. Okay.
Correct.
Okay.
Yeah, this is pure zero shot in some sense. So I'll talk about the nuances of this kind of design later on, but it does emphasize like this notion of like you only update using gradient steps. There's no in-context learning. The benefit here at least is like then you can be really lazy and shove in any X that's like of arbitrary length, right? You don't have to deal with like compressing X's so that it can do in-context learning, which is a huge problem for like a lot of applications like combinatorics, right? It's very hard to like compress X in many applications. Yeah.
One other question is if you don't pre-train on the internet data, if you don't use some custom LLM, what do you pre-train on?
Nothing. Or like I'll I'll talk about that later. It'll make more sense. Like technically nothing, but I do sort of train it on the actual XY data itself later on. So let me just talk about that.
Yes.
Yeah, so for answer training, right, like, of course, using Google Vizier data is the most convenient form, right? Unfortunately, we cannot open source this because of legal concerns. I'm sorry about that. And the unfortunate thing is, like, I don't think there's a huge, data set out there right now that replicates this kind of thing. So unfortunately, yeah, it is kind of closed source research. But yeah, so like using Visier data as a convenient source of regression data, right? It contains data from AutoML, chemistry, productions, right? So there's a wide source of data, like, and it's like at the law, right? Like this 14K distinct users, 70 million studies, and so forth. And just as a recap, in Visier, basically it's a typical optimization API. You can specify a flat search space with the different, parameter types. But it allows conditional parameters, which means that right, some parameters are turned on or off based on what the parent might be, right? So for example, if your parent parameter is like SG or atom, then like momentum parameters and things like beta are only turned on for atom, but they're not turned on for SG. That makes the case that like trials might have different numbers of parameters, right? And so this is already going to cause problems for baseline regressors like MLPs, because you have now like variable length parameters in different trials that you have to deal with pre-processing, right? We don't have to deal with that because we just JSON the dictionary. Yeah, and so Visier metadata, right? How like it's going to use it for transferability is like, well, Visier metadata contains like title, owner, descriptions, etc. So transferability sources would be maybe like you have a single user and they run very similar experiments, right? But you might also have a different user and they still run similar experiments. Like everybody is training a resident on CFAR10, right? You might have similar parameters over different experiments, like learning rate, right? Everybody uses learning rate on different settings. And lastly, you might have, people might send in the description or freeform metadata, like some users actually send in their code or file locations, right? This might be useful. So to give you a concrete example, this is what it looks like. So for some AutoML data, right, the X is just like regular hyperparameters, as you can see. And then the M is like, I have to redact something for like privacy, but otherwise like the M, right, has things like the objective name is like cross entropy, or it has some other data like task type, multi-class classification, right? Another case would be like, there's another team that studies like optimizer learning rates and things like that. So right, X is a bunch of learning rate parameters, and the M, right, might be like, oh, it says the title is like LM1B transformer, right? And then the objective is like the cross entropy loss, right? But even for like proteins, right? In this case, there is no English name for the parameters. They're just like numbers and then corresponding to some categories. And even here, it might work, right? Yeah, lastly, here's just another like AutoML case, right? Very similar to before, just giving examples. We also do want to, have toy experiments, since like we cannot control the data distribution of the offline data, right? Like we can't control how saturated the search space is. So we're gonna try some toy experiments, right? Using synthetic BBOE data, where we're gonna say, okay, make some giant multitask augmentation of it by like saying, for any BBOE function, we're gonna take a random shift and shift the input, right? It's for meta learning. And at least for the metadata, it will contain basically the parameters that define the objective, right? It's like that'd be the function name, the dimension, and the shift, right? With these, you can actually technically get out the function behavior, right? So sphere function, dimension equals 3, shift is something, right? Yeah, and as for baselines, right, we're going to use Gaussian process, Visier default, random forest, XGBoost, MLPs. These all, as I said, require you to make the X turn into a fixed length vector between 0 and 1. That is a very deep problem for a lot of combinatorial like situations and even conditional situations. But as a caveat, I think I'm not trying to start a regression fight. I do think like this is a very sensitive topic for AutoML researchers. I just, like we tune them and it's like they look fine, but like Probably they could be tuned even better, but I'm not trying to start a fight on that. Okay, I'm not trying to say our regressor is like the best in the world, right? But yeah.
One second, Richard. Can you go back to? I
Yeah.
fully understand that you don't want to figure out what's the best model you want to over optimize, but I still like to understand how you actually encode it into X, because
Okay, yeah.
it seems to be like a
Question.
super high dimensional space if you
Yeah,
Oh.
so for flat parameters, right, the floating point gets, because the user specifies the search space bounds, you can technically normalize the floating point parameter into 0, 1, right? This is a similar case for integers. Yeah, but for, let's say, categoricals, you'll turn in the one-hot embedded vectors based on the number of categories, right? So like that should be fine.
And
So
but how do you do that across users? So if user A optimizes the learning rate and user B has an experiment optimizing, I don't know, momentum or something, do you have then essentially two different parameters in your, or is it then two different entries in your X?
Yeah, so that's inherently problem, is like a user has this study, we have to specify this kind of mapping for them. The user has this other study, we have to specify a different mapping. Therefore, it's very hard to multitask learn from any of these, right? That's the actual limitation of these baselines.
Okay.
Because like the feature dimensions, let's say, are even like completely different many times.
Okay, right? So essentially for each task you have one of those regressor models.
Yeah, so these baselines can only do single task.
Right. Yeah, that makes sense. Yeah.
Yeah. Yeah. So yeah, our evaluation protocol would be just like computer normalized mean average error, right? I have to normalize it because right, different objectives have different y scales. Like CFR times between 0 and 1, whereas BBB is like a gigantic number, right? I have to normalize it so like there's some sort of notion of like you can aggregate these results somehow, right? Also, important point is that the fact that it matters, the language model is learning a distribution over the y space actually. So this metric only works for a pointwise prediction. So what I have to do is like sample 64 times from the this numeric distribution that the language model is making, and I have to take the median of that to aggregate to get a pointwise estimate. I'll explain why median is actually better than, let's say, mean or something. Okay. Yeah. Any other questions before experiments? Okay. Yeah. So the key questions are like, okay, can the language model simultaneously regress on multiple tasks, right? That's the very first question, why we're doing all of this in the first place, right? Can it do it over different search spaces and numeric scales? A second one is multitask training even useful, right? Like if I'm going to evaluate on CFR10 studies, why am I training on ImageNet studies? What is the benefit to that, right? And lastly, can fine-tuning deal with unseen tasks, right? Because I get a lot of this, like, you need to be able to at least also adapt to new data, right? And also, does this pre-trained knowledge really carry over, right? So so let's just talk about the first question, simultaneous regression, right? So, suppose I pre-trained the model over the gigantic BBB data, and then now I evaluate it on some new shift, essentially, right? I just wanted to plot basically like how good it is at precisely predicting the y values simultaneously, right? So you'll see on this case, the y-axis, the scales for every different function, right, can be different, right? So for example, at the top row, the step ellipsoidal, right, is like between 500 and 540. But the middle guy is between like some other range. And then last one is like some Rosenbrock is like huge range, right? Like 10,000 range, right? And it turns out that, well, the model can simultaneously regress on everybody because we're using absolute, these sort of absolute serializations, and it's being prompted by the M, which is like the name of the function, right? So it can do all these based on what is the M and what is the X, right? And you can sort of see it captures basically the shape of almost like all these functions, right? Whether it's like spiky or curvy or whatever, right? Yeah, and as an aside, is like, note that the language model is actually capturing distribution of the y values, not just the point-one estimate. So for example, let's suppose that I flip the y value, randomly flip the sign of the y value, right? just make this distribution bimodal, right? So then what happens? Well, the language model still is able to capture that after training. It's able to capture this kind of bimodality, right? Now you have basically either like it knows that like it's either one of two curves, and you did not need to specify the number of ensembles or anything. Like the model doesn't need to know that. It can capture. It's like non-parametric, and it can capture these kind of modes. Whereas like normal baseline regressors, they can also do this, but you have to specify things like the number of ensembles or something, right? This is non-parametric setting might be useful later on. As another question is like, well, what about real world objectives, right? So I handpicked like 8 objectives, each with like maybe somewhat different search spaces, right? So for example, like CFR10 has like 4 double parameters, but protein design has like 60 categories, right? These are wildly different search spaces. But as you can see here with the plot, these diagonal plots, right, where like you're checking the prediction versus the y-axis, right? Like the model is still roughly able to get that diagonal like regression on, right? And you also see that the fact that, right, like many of these objectives also have different y scales, right? So it's like based on whatever the M prompt is for it to like identify which study am I on, it can still figure out what the roughly the right scales are, right? The y values. Yeah. Yeah. So now let me go into the second question then. So why on earth are we doing this multitask training at all, right? What's the benefit, right? If I only evaluate on f of x, why would training on f prime of x even help? So in our experiment, what we did was, okay, let's specify a fixed evaluation set, right? That we're going to keep fixed for the entire experiment. But let's vary the let me actually point, by this point, let me use the cursor, right? Like, oops. Yeah, this is a better red cursor, right? So the idea here is that like, despite the fact that the model is going to see more and more data that's like f primes, right? Different studies that might have different search spaces, different objectives, whatever, it still somehow benefits our evaluation performance on this fixed set, right? This fixed set. So there's some notion of like, there's some sort of synergy happening where like, it is beneficial essentially to train on ImageNet studies, despite the fact that I'm still evaluating only on a CFAR10, right? That's the analogy here, right? There is some sort of synergy going on. And for BBOBs, right? For BBOBs, like because of how you set up as a toy task, you can sort of say that like the function is essentially now like also a function of M, the specifications of like a BBOB objective, right? And this sort of is saying like there's not really a notion of X or M anymore. They're all just prompts in one way or another, right? But anyways, right, we did take a look at this, right? So let's say we vary M and then like evaluate on an unseen shift, right? So this is some a form of like out of distribution meta generalization in some sense, right? And you'll see again, like the fact of the matter is it's training on other studies' data, but that's improving its evaluation performance on this fixed evaluation study, right? Right. So yeah, that's what's happening. Yeah. So let's take a look at more like aggregate metrics over a wide variety of domains, right? So I did specify essentially like, right, you saw the BBOB and I showed you basically the AutoML. I showed it for a bunch of different domains, right? And so so let me clarify first. So the first 4 are the single task baselines, okay? And then the gray one is basically single task LM. This means that the model is only going to see the data from that single task, the training trial from that single task, and of course evaluate on the test trials from that single task, right? This is like saying I'm going to there's no like synergy multitask training, whatever, right? And then the black bar is multitask training. So you can sort of say that the first 5 are in apples to apples comparison, okay? So then the question is, how well does the LM do here, right? I'd say it's doing not bad, right? if you take a look at what's going on here, some of these cases, right, even the single task is outperforming these other baselines, right? That's, for me, that was mind-blowing, because like it's quite a bit of limited data already, right? Single task only has like 800 trials for training, not like these gigantic, thousands and hundreds of thousands of trials in multitask case. It only has 800 trials or something like that, and it still manages to beat these other baselines, which like have a better inductive bias, in all honesty, arguably, than the language model, which like doesn't understand what numbers are, does not understand like what names are, etc. Right? And that's what baffled me, right?
Just to clarify, so this is the same model for the single task and the multitask model. So it's just the same.
It's the
architecture.
same 12 layer, just like different data, different data training. Yeah. So yeah, you'll also see this on another case, right? Like some other domain, like another AutoML data set, where like this gray bar is below the the blue bar, right? The next best regressor. And you also see this case here, right? It's like saying single task training is already not that bad. Some practitioner can already stick this model into their single task regression and still get pretty reasonable results, right? And a pattern I saw was like this outperformance actually happens a lot of times with conditional search spaces. So to just say, like, roughly speaking, when I add a parentheses here, this basically means like how big the search space is, and if I add a parentheses, it means like it's a conditional search space, right? So Google AutoML and Vertex AI AutoML are both conditional search spaces, and that's what's corresponding to exactly these outperformances on all their baselines, right? Yeah, but of course, this gray bar is not always going to beat the MLP for other cases, and a lot of times this is because they're flat search spaces, right? So this is some sort of saying at least like this model is at least good for dealing with these combinatorial kind of X's, right? Like conditional search spaces, where like whereas baseline regressors you have to deal with like fixed links and all that stuff, right? It's very tough, right? Now, of course, multitask beats single task, right? The more data you send in, despite the fact that this data is not necessarily the same exact functions you're writing, right? It still helps, right? So the black bar is always lower than the gray bar, right? One tidbit what I saw was like, unfortunately, this for here, the black bar still did not beat the baseline, right? And I want to know why. That's what I'm saying, like multitask training still does not beat single task MLP. And so I took a look at this for bid simulation. And it turns out that this can be explained by the fact that this guy has a very highly saturated search space, right? The average trials per space is like 700, whereas its search space size is 400, right? So it's basically saying the search space is already saturated, right, with tons and tons of data. You don't need additional data from other studies, right? The MLP is like, we're not in a data limited scenario here. So the MLP is doing pretty well, even in a single task case, right? That's the saying, yeah, multitask is better if like there's a data deficiency going on somewhere, right? Yeah. So yeah, that's what's happening. Another case is like, right, does text help? So the idea here is that, like, suppose I did an A/B test where I basically anonymized the prompts, right? So what I'm gonna do is like, instead of having the language model see things like English names like batch size, I'm gonna hash it, right? Depending on the study, right? So I'm gonna hash things like categorical values too. I'm gonna hash literally everything, right? So in this scenario, the model, like theoretically speaking, it's still possible to train your model over this kind of data, because this hash is only dependent on the study, right? So it's like it can still identify the study, but then there's no correlation between like f and f prime of x. There's no correlation between different studies, right? I've really destroyed that. Then what happens, right? And so right here, the numbers for the original case, right, where it's not anonymized, but after anonymization, well, we found that, right, the model can still train for most cases, right? So like this scenario makes sense, but the evaluation performance is way worse, right? The idea is like you've lost the helpfulness of multitask training. And a funny thing is that like actually their model refused to train actually once I moved to a gigantic BBOE data set. It's sort of saying like, this data set has no more correlations. I don't want to memorize the entire data set or something. Like I refuse to train at all, right? It is interesting how these models like work. Yeah. So lastly, right, the idea here, the third most important question is how do I adapt to new data, right? So as I said, we're gonna do some local fine tuning, right, against these new trials. So, right, the classic GPT trick is to pre-train then fine tune. And so what I'm gonna do is, okay, so I'm gonna evaluate on unseen Visier studies, right? So my pre-trained model is gonna be trained on like all the data before March 31st, But I'm gonna evaluate on new studies after March 31st, right? There's no way the model could have seen those new data, right? But the model can fine-tune over the training trials of each study, right? Like to make it fair, of course. And you know, just like for data cleaning, I'm gonna only evaluate on distinct users because a lot of users, right? There's like some massive power user of Visier. I don't want to like saturate our research with that, right? So what happens? So the first thing here is that, right, I just want to compare against essentially single task, right, where the model has no prior knowledge about anything, and it's gonna train over the training trials of an unseen study, versus pre-trained then fine-tune, which is basically saying now the model is warm started with the pre-trained checkpoint, but it's going to do the exact same thing. It's going to do some gradient steps to update against the unseen trials of this new unseen study, right? So what happens, right? So as you can see here in the green case, there is positive transfer, right? And this can be significant, right? Your pre-trained knowledge carries over to new studies, right? There's a pretty huge gap going on here where like, because the model has been pre-trained, the red part, right? The red part here, because the model has been pre-trained with some knowledge already, therefore it already understands the like sort of format and distributions and whatever of people's objectives. So this knowledge carries over, and then even after fine-tuning, right? So that's that. But there are cases of negative transfer here in the purple case, where actually the single task does better, right? Like sometimes this pre-trained knowledge is even worse, actually makes you worse, right? For some reason. So I actually investigated this like in a toy setting. When do we have positive or negative fine-tuning transfer? So the idea here is, okay, suppose, let's say we already have a fixed evaluation settings like the AutoML data, and I'm gonna vary the possible pre-trained checkpoints, right? So one can be like none, which means that this turns back into a single task case. Or I can pre-train it over all the BBOE functions, but fine-tune it over AutoML data, right? Or, let's say just for sake of clarity, I also have a pre-trained AutoML checkpoint itself. And lastly, let's have a checkpoint pre-trained on entire Visier data set, which is much bigger, right? And so what you'll see here is that, right, none, if you just pre-train from scratch, of course, like, because it's never seen the trials of this unseen study, right? Like it's a zero-shot regressor. Of course, it's going to fail, right? But after fine-tuning on some training data, its performance is, let's say, 0.2, right? But for BBOB, right, it's been pre-trained on BBOB functions, but after fine-tuning on AutoML data, there's actually negative transfer going on here, right? Like it reduces the error, of course, but it's actually doing worse than like had you not warm started at all with the BBOE checkpoint, right? This means that some sense like the BBOE functions are way too far away for you to like for some sort of knowledge transfer to happen, right? But at least you do see this kind of like positive case where AutoML itself, right? AutoML itself, like of course, like they're the same, right? You don't need to fine tune. But then if you pre-train on the entire Visier data set and then focus in on the AutoML data set, then actually you do see a drop in error, and this error matches with the AutoML, right? So it's basically saying I could possibly pre-train the model over all the entire Visier data, and now it like can be used for any other standard tuning regression, right, case, and there might be it might help. Yeah. So are we low on time? I mean, let me just quick. By the way, is there any questions?
You were fine-tuning with LoRa, right?
No LoRa. Actually, it was just pure raw gradients because the model is so small anyways.
Okay.
Yeah.
I'm wondering, hi Richard. So I'm just wondering, for the training loss, did you just use the cross entropy loss, or you?
Yes. Yeah, it was pure cross entropy standard GPD setting.
Okay, so in the ablation, did you try some, I don't know, regression loss, like mean square errors, since you know it's a number, real number, right?
Right. This is a great question, and it's a very nuanced question. So the reason we did not proceed in the MSE error, making that an MSE error loss, it's because then number one, you have to normalize your Y values again per study, right? Otherwise, training might not happen because the Y values are so wildly different per study, right? And then now that goes back in the idea of like now I'm normalizing stuff, which messes up this like idealistic notion of like absolute representations, right? That's the first point. The second one is like, to make this work for an MLP, you have to, take the encoder, attach it with an MLP, right? And then you change your loss entirely and stuff like that. Yeah, we did not try that because it's very hard to do if you had like a bigger LLM, right? Like most packages don't support this, and we're like, that makes the work a bit too specific. Yeah. So TLDR, we did not try MSE loss. I do agree that is important to try, but
Yeah.
like a lot of design choices that forbid this.
Yeah.
Yeah.
Maybe not MSE, maybe some percentage error. I don't know. Try to
Anyway.
mitigate that issues. Yeah.
Yeah. But I mean, like for cross entropy, you can, given our current tokenization, you can sort of like upweight the most important tokens, like the signs and the exponent tokens, right? And like there are ways to improve the performance even on the cross entropy case. And it turns out that like there's been a recent work also saying that like cross entropy losses actually can still be really good for even numeric regression. Surprisingly, right? Like there's been a lot of cases where like people just started binning tokens, right? These categorical tokens that have no numeric continuity, and it still works very well. And so like, yeah.
Yeah, that's true. We also observe something like that.
Yeah, so I'm wondering if like it could be a paradigm shift where everybody just started using cross entropy losses instead of like MSE losses from now on, because there are a lot of benefits. Yeah. So yeah, any other questions? I mean, even on that cross entropy, it's like MSE essentially is like forcing you to learn maybe like a point-wise estimate. But cross entropy might be slightly better maybe for learning like a general distribution over the Y values, possibly, but don't quote me on that one as well. But yeah. Any other questions? Okay. Yeah, so I mean, just these are just small ablations, right? As I think you've asked, like we did try like different tokenizations of the Y values, and everything made sense, right? Like this is the worst possible tokenization ever because now you have like 10,000 bins, right? You've merged all the mantisses and the signs together. You have basically 18,000 or like tens of thousands of categorical bins. So of course, right, if you try a single task, the model doesn't have time to sort of like massage those token embeddings very much. Although surprisingly, if you did the multitask, right, with large amounts of data, these bins don't really matter even, right? Apparently, they still have the same error, but like for single tasks, for data deficient cases, it does matter, right? Another case is yeah. Here's why we chose median instead of max or mean aggregation. It just turned out to be this actually reduced the error the most, and we think it's possible is because median is actually more outlier robust than all these other cases. Yeah, because like if you use the mean, like it's not outlier robust, and because and the model currently you've allowed it to output any Y value within like basically all of the real number line, right? So of course you might have some gigantic outlier out there. If you take the mean, this is like terrible. question?
Yeah, have you tested something like the cut mean, where you basically first take the quantiles, like the 25 to 75% quantile, and then take the mean? So to get rid of outliers this way?
Oh yeah, that's a good. I mean, yeah, it's worth a shot. Yeah, thanks. That's a good idea. Yeah, but that was the issue, right? It was just avoiding outliers. So yeah, that might be helpful. Yeah. Yeah, and of course, like this was the observation before. It's just like when does multitask training help? Right, we compare it against the MLP. So this is just like the difference between the gap in performance between the MLP and the multitask LLM, right? And so you see, it spikes when the number of training trials is limited, right, in the 50 range. But it reduces over time because, well, at that point you've saturated the search space that you don't need multitask regression. You're not in a data deficient case anymore, right? Yeah. So those are basic ablations. So in conclusion, I think like there's one thing. Yeah, let me talk about this. So there's a philosophical paradigm going on here, which I think is important, is that in-context learning is not the only way to absorb your XY values. And it has a lot of limitations, such as like, you now have a memory blow-up constraint. You have to compress your X's. This can only therefore be used for flat search spaces, not combinatorial objects, right? It causes a lot of problems. But with gradients, right, there's an unbounded limit for absorbing these XY pairs, really, right? Because gradients don't have a memory, size blow up that's dependent on the data, right? And also it allows you to easier format your X's, right? Using like JSON, you don't need to compress it anymore to stick it into like, oh, XY in context learning, right? So it's an analogy to like, the argument between MLPs and GPs, right? MLPs, they use gradient-based updates to aggregate data, and you can like MLP can technically train on infinite data, whereas GPs have some sort of memory limit, right? Because they're in context. Yeah. So many improvements on the OmniPred side, right? You can weight the cross entropys, like I said. You can upweight the sign and exponent. You can have better X tokenizations because by default, the tokenizer actually is not that like good with numbers, right? Like by default, it actually tokenizes numbers in a weird way where it's not digit by digit actually. You can have better warm starts like English pre-training possibly to decode the X's first. This is actually very used in the biology literature. They sort of pre-train protein models to first predict the proteins themselves, and then use it somehow for like Y value prediction, right? But yeah, I do think that this is this opens doors to new applications like graphs, combinatorial X language code, which I think maybe the AutoML community could be studying more, right? Going into things like how do you search over programs, and then how do you search over programs efficiently with some regressor guided search, or things like that. And right, related to AutoML works is like possibly new benchmarks, right? Reward models simulate human ratings. Well, these language model surrogates that I'm talking about simulate realistic objectives, right? You can have some sort of so that like people stop benchmarking over like just BBOB functions every day on every paper, and maybe we have even more realistic simulators of everything, right? Yeah, but there's more links in this slide, but yeah, that's the end of my talk. Thanks.